Let's imagine that you are on a huge turntable, like a record player for giants. Here it is drawn in blue. You are the green oval. As you ride on the turntable, you have a red ball with you. And for the sake of argument, let's say that the turntable is spinning counterclockwise. What will it look like when you throw the ball? Now this diagram is showing the viewpoint from someone high overhead looking down on the situation. At this moment, the ball is moving this way, as are you, but we're really only going to concern ourselves with the ball. So the ball is going that way, and then you throw the ball towards the center. And so there are two velocities here. There's the radial velocity, that is in the direction of the radius towards the center of the circle, and then there is the tangential or sideways velocity that was due to the rotation of the turntable. And so we have two components of the velocity the ball does, and therefore the ball is really going to go in that diagonal direction that I just drew. So the ball will travel in a straight line like that. However, you, being on the turntable, are not going to see it that way. And that is because on the turntable, your coordinate system or your reference frame is itself rotating. So to you, instead of the ball going in a straight line, it will look like the ball does that. It looks like it will curve. And one way to think about that is to think about what are the relative velocities of the ball sideways compared to the tangential movement of the platform itself, of the turntable. What part of the turntable is moving the fastest? That would be the edge of the turntable. And what part is moving the slowest? Well, in fact, the center of the turntable isn't moving at all. Right outside that part of the surface is moving very slowly, kind of halfway is moving at a medium speed, and the edge of the turntable is the part that is moving the fastest. The ball is moving sideways like that due to the spin of the turntable, and then when you throw it towards the center, as it goes inwards here, it is moving faster than that bit of the surface of the turntable. And so from the perspective of the turntable, the ball will appear to go like that, to be here. As the ball goes even further inwards, it is moving even faster compared to the speed of the turntable here. So from your perspective, the ball will appear to curve like that. So with the turntable turning counterclockwise, the ball will appear to turn to the right. If, on the other hand, the turntable is turning clockwise, like this, then from your perspective, you are turning to the left, and the ball will appear to curve to the left. Now, the Coriolis effect is often brought up in discussions of meteorology, that is, weather systems, and specifically hurricanes or typhoons or cyclones. These are all different words for the same thing. All of those words refer to very strong low pressure systems on the Earth. Here is a sketch of the Earth, and we're looking at it from the side, so to speak. We have the North Pole at the top, the South Pole at the bottom. The line through the center is the Earth's equator. And this L is the symbol that meteorologists use on those weather maps to indicate a low pressure system. Now, before we talk about the hurricane itself, let's just talk about the surface of the Earth. Just like for the giant turntable, the farther you are from the axis, the faster you're moving. And what's the point on the Earth that is furthest from the axis is the equator. Again, you have to keep in mind that this is a three-dimensional object, and the axis runs through the center of the spherical Earth. All these points along the equator are one Earth radius from the axis, whereas points at the North Pole or at the South Pole are on the axis. The points that are furthest from the axis are on the equator. So those points are moving to the east that is, the Earth spins towards the east, these points are moving towards the east the fastest, whereas points in the mid-latitudes are moving to the east at a medium speed, and up in the Arctic they're moving quite slow. So that's just talking about the speed of different points or different latitude zones on the Earth. Now let's take a look at our low pressure system. In addition to the L, which is indicating the center of the low pressure system, I've also drawn two blue dots, and these are meant to represent small pockets of air, certain volume or mass of air located to the south and to the north of this low pressure system. Low pressure acts like a vacuum, and it is going to try to suck in these air masses. That is, low pressure is going to draw air towards the center. This air mass here is moving to the east because it's going with the Earth. But as it is also drawn to the north by the low pressure here, it will be passing over land that is moving slower than the air mass was here near the equator. And so as it goes northwards over land that is moving slower, from the perspective of us here on the Earth, standing on the surface, it will appear that it turns this way. That is, from the perspective of the air particles or the air mass here, it's turning to the right. This air mass here to the north of the low pressure, as it gets drawn to the south, it will turn to the west. Again, it's really moving to the east, but it's moving to the east slower than the land over which it is now traveling. And so from the perspective of the land, from the perspective of the coordinate system that is rotating with the Earth, then it will appear to lag behind and go to the west. And so we are left with a pressure system that swirls around the low in a counterclockwise sense. In the southern hemisphere, the reasoning is very similar. You have a low pressure system. It is going to draw air in. This air mass right here is moving to the east very fast because it is near the equator. And as it gets drawn to the south, however, that inertia will carry it ahead of the slower moving surface of land over which it passes. So it will curve to the left. And to the left, when I say to the left, I mean from the perspective of this air mass. It's traveling this way, and imagine you're driving a car and you're facing down and to the right in the diagram. That would constitute a left-hand turn. This air mass here is going to be drawn northwards. It's moving relatively slowly because it's at the mid-latitudes. As it is drawn towards the equator, where the land is moving faster, it will lag behind. It will also turn to the left. But if you look carefully at what's happened here, this one's now moving this way, this one's moving this way. This is an air circulation now going clockwise around that low pressure. So in these low pressure systems, cyclones, hurricanes, typhoons, whatever word you want to use, the circulation is counterclockwise in the northern hemisphere, clockwise in the southern hemisphere.